Hello, this is a lecture on correlations. And you can see that correlations are tools for measuring relationships among variables or between variables in the case we'll be working with today. You can see this little word relation also in correlation. When you're trying to determine if correlation has been done or will be done, you'll often see that word relationship. So we're looking at the relationship typically for this first part between two variables, and they both have to be continuous or ordinal variables. You could run a correlation on a nominal variable, but you're going to get strange looking data. And so we typically save correlations for these continuous variables with numeric responses that have at least an order or have a number of possible points for a person. And so when we're looking at relationships between variables, we're trying to see whether they tend to vary together. So either in the same direction or in the opposite direction. And as we go through this, we're going to take a look today at several characteristics of the correlation. We're going to look at how we depict a correlation, at what shapes a correlation can take, how we can know the strength of a correlation, how we can interpret it, and some cautionary notes. And this content would be delivered in two parts, one strictly on this whiteboard and the second part on slides. So let's give some examples here. Let's imagine that we have gathered from a number of different students 2 data points. Student 1, student 2, student 3, and so forth. And the 2 data points represent, and let me write them here, represent study hours per week. And the second variable represents grades. And from each student, we got 2 data points. I'm going to write them in parentheses rather than columns this time, because you'd often see them that way if you're working by hand. So the first person studied 10 hours a week, and their grade point average was a 3.0. The second student studied 12 hours a week, and their grade point average was 3.5. The third student studied 4 hours per week, and their grade point average was 2.5, and so forth. So we have a continuation to student X. And so we have, as you can see, a set of coordinates, and you might be familiar with these in the past. And what we do when we're working with correlations is we want to plot the graph, just like you may have done in some long ago math class. And so we're going to use what we call a scatter plot. And the scatter plot starts out with somewhat evenly equal in proportion y-axis and x-axis. One variable goes on the x-axis, whichever we think is maybe more likely to predict, or the one that precedes in time. In this case, I think I'm going to put study hours. And the y-axis is the other variable. We mark the points. Let's say someone could study 0, someone might go up to 20. We could try this for the range. We'll put our 10 in the middle. And on grades, the same thing. A GPA can be 0, and it can go at Diné College as high as 4 with a 2 in the middle. And by grades, we're looking at GPA, your grade point average. So let's plot this for student. 10 hours per week and a 3.0 GPA. We would, of course, just find the 3 would be about here, the 10 would be there, and we'd plot that person's point. And for this moment, I'm going to write in the coordinates. The second person is 12, which is going to be right around here, and a 3.5, which will be a little bit higher. There we go. And the third person listed so far has 4 study hours a week. That's right about here, and a GPA of 2.5. And I won't write those in this case. And so let's imagine we gathered up data for all of these students, and now we're at the end and we've plotted all their points. So I'm just going to draw a bunch of more points in here as if these are representing students from whom we have gathered data about weekly study hours and GPA. And when you look at what we have here, you can see that the plots tend to take on a direction. You can see that they're moving in an upward direction. And they also take on a shape. You can see it's easy to draw a straight line through this relationship. So first off, we have here a scatter plot. The scatter plot can show the direction and strength of the distribution. We'll look more at the strength in a moment. We already looked at the direction in that red arrow. And we can see here that this is a linear, I'll write this in capitals because not all relationships are linear, but this one is linear. And it means we can draw a straight line through the data field. A straight line can represent the data. Now, in this case, we have the straight line. It seems to represent the data. We draw this line, the line of best fit, through the point where it covers most, the point where it comes closest to the greatest number of points. So that's how we try and plot the line. It's called the line of best fit or a regression line, depending on how you're using the calculation. And so we can use this line, I'll keep with the red here representing the line, to tell the direction of the relationship. And the direction can be one of two things. It can either be positive. The line goes in an upward direction, or it can be negative. The line goes in a downward direction. Now, make note, this is not anything indicating good or bad. This is just the way that that line filled out. So with that said, let's look at an example of a relationship that could possibly be negative. So I'm going to give another example here. I'm going to give an example of sleep hours and work hours. Sleep hours and work hours. I'll put them in parentheses the way the coordinates will be. And let's imagine that student 1 over the course of a week had average number of sleep hours of, let's say, 8.5. And let's say they had 0 work hours. They were a student. And let's say student 2 had sleep hours average per night of 6.5, and their work hours were 25 hours that week. Student 3 had average hours of sleep per night as 7, and they worked 15 hours over the course of that week, and so on till we get to student X. So let's plot these out the same way. We'll draw our two axes and we'll make them approximately equal in length. On our x-axis, I'm going to put the, I think maybe work hours would predict sleep hours a little better than the other way around. So I'm going to put work hours here. Let's imagine that they can go from 0 to, I imagine 60 is possible. In this data set, for the sake of our demonstration, I'm going to stay with 30. Just so that I can stay on the page here, but you'd want to address your data in here. And then we have sleep hours. I don't think anyone could get 0 hours of sleep on average a night for the course of a week, but maybe as low as 4, possibly lower. Our data don't represent that the way they are here, and maybe up to an average of 10 hours per night. And let's put our 7 in the middle here. And in the middle here, we're going to have our 15. And we know that on our y-axis, we have decided to put, actually this time around, our sleep hours. And typically, we would list our x variable first and our y variable second. So I'm just going to draw an arrow there reminding us that normally these would be separate. So, in fact, I should just do it here so as to avoid confusion. But I'm not going to. I'm just going to draw the arrow each time. So in this first person, they have 0 on their work hours and 8.5 on their sleep. So their point is going to be, right around here. The second person has 25. Once again, I'm drawing these arrows. They should be switched. 25 on their work hours, and their sleep is 6.5. So that's going to plot out right around here. And the next student is going to have 15 on their work hours and 7 on their sleep hours. The point is going to be right around there. And if we continue to plot points out for all of these other students, maybe we would have revealed a relationship like this, suggesting that as the number of work hours increased, the number of sleep hours decreased. So maybe we'd get something like that. In this case, we can still draw a straight line through the points, but this time it's going in a downward direction. So we can say this is still linear because we get that straight line, but we would also say that this is a negative relationship, and it doesn't mean bad. Let's write that down here. Doesn't mean bad in the sense of emotionally bad or anything like that. It just means as one goes up, as one variable increases, the other variable decreases. That's all that means. So I've mentioned that there are a couple of different shapes that we can have in this kind of a relationship. And we've already talked about a linear relationship. So let's identify these down here. Shapes. We can have a linear relationship. And that just means a straight line can fit the distribution. We could also have a zero relationship. That means we just can't make any heads or tails of any of it. There just doesn't seem to be anything going on. And that might look something like this. Here's our x variable, our y variable. We won't name them just yet, but the points might just be all over the map. We can't really even tell if a straight line would fit the points well. It's just all over the place. In fact, you might even say best you could do is draw a circle around it. And that just means there's nothing going on. Nothing going on. No relationship. Whoops, no relationship. And that might be something ridiculous, like the number of pairs of shoes you own and the length of your fingernails. You know, we wouldn't expect any relationship there. We would call it a zero relationship. But we can also have something called a curvilinear relationship. And that means that the best line that fits the data is curved. There are many different ways this can appear, and I'm going to give you just one example. I'm going to give you an example of like arousal and performance, which is a typical curvilinear relationship. So we will put here on the y-axis, we're going to put performance. On a particular task, and on the x-axis, we're going to put arousal. And I'll write these on the side and define them for you a moment. So our x is going to be arousal. And so x variable always first, arousal. We can think of this as being like psychological arousal with sympathetic nervous system activation. So your heart's beating faster. You can, that can continue, that arousal variable can be on a whole range. Like when you're really tired, you're not aroused at all. You could be really just lethargic and sleepy, and you might think about your performance, let's say on a cognitive task or on a speech or something. If you're in a really low state of arousal, you're really sleepy, you've barely woken up, your performance wouldn't be that great. So let's imagine that this is our performance on some cognitive task. It ranges from lowest to highest. You're taking this test right now. If you have low arousal, maybe you're not going to do that well. You're just too drowsy. You feel like you need to get coffee. You could also have really high arousal. You drank way too much coffee. You're jittery, you're jumpy. You can feel your heart racing. You're thinking too fast. You're not thinking carefully. You can think of a high arousal state as also maybe having a poor performance. Most of the time, we want to be somewhere in the middle here. We want to have a middle range of arousal. Have a cup of coffee, but not 5 cups of coffee. And when we're at this middle level of arousal, that's when our performance tends to be at its best. And so if we plot a number of points, we tend to get a distribution that looks something like this. If we measure people's arousal and we measure their performance, maybe the distribution looks like this. And we find that the best line to cover all the points can't be straight. It's got to be curved, and maybe it looks something like this. And we call this a curvilinear relationship. And there are other common relationships like this. We won't go through this now. That's not the purpose of this course. So those are the shapes that these relationships can take. Now, we are able to also detect the strength of a relationship like this. And strength is determined by how close the points are to the line of best fit or to the regression line. So let's write a little bit here. Strength is the closeness, nearness of points to the line. All right, so it might look something like this. If this line were really perfectly drawn, it would be near to the greatest number of points, and we would be conceptually taking the average distance. Let's put a few more here because the line isn't quite placed right. You would never do this with real research. You'd always have actual data. But what we'd be looking at are all of these distances between this line and each individual point. And so conceptually, that's what this is. The closer the points are to the line, the higher the strength. So let's look at this a little bit over here. So strength the closeness of the points to the line. And it is determined, it's measured statistically by something we called a Pearson R value, or sometimes called an R coefficient or an R score. And an R score can range anywhere from 0 to 1. So this is the continuum for strength. The lowest possible score is 0. The highest possible score is 1. It cannot go above 1. And right in the middle here, we'd have a 0.5. We'd have a 0.8 right around here. We'd have a 0.2 right around here. And we rate these scores just like we do the scores for effect size. 0.2 is considered weak. 0.5 is considered moderate, and 0.8 is considered strong. And this 0 we've already talked about. It's just considered 0, a 0 relationship, and a score of 1 is a perfect relationship. So we have two measures that we'll give when we're using quantitative factors talking about correlation. We have strength, which we've just discussed, and we have direction, which is just the the upward or downward tendency of the line in a linear relationship. Someone's here. Hold on a sec.